Hello, and welcome to CodeRage. My name is Robert Love. Today's session is titled Introduction to Encryption, Understanding Security Algorithm Use Cases. The basic goal of this session is to let you understand what different types of algorithms there are and how to understand which one you'd use and when. But I want to start off with a small disclaimer. I don't pretend to be a security expert. I work with these types of experts every day. I am a developer who is highly interested in security, and I've seen misapplications of security technologies leading to a false sense of security. My goal with this session is to help know what algorithm to pick and when, giving you direction on ways to implement these algorithms in a secure way. In this session, we'll start with a little introduction to cryptography. Then we'll cover hashes. Then we'll deal with symmetric key. And then we'll deal with public key, or another word for this is asymmetric key encryption or cryptography. The desire to keep data or a message secret has existed for a very long time. Often these methods keep our data secure have been figured out, as you might see like the Enigma machine here. And more sophisticated methods have to be developed. As a child, I remember playing with the secret decoder ring. It was not long after I'd been playing with it that I wondered, could I figure out how this coded message works and figure out what somebody else might have wrote? Well, the Caesar cipher is what the secret decoder ring uses, and it was developed in ancient Rome. It takes a given alphabet and rotates all the characters by X number of digits. And in this case, we've rotated it 4 digits. Well, as a kid, I learned how to break these codes really quickly. And I would look for common letters in the English alphabet with common words. The puzzle books that I used as a kid to play with these became more and more difficult by randomizing the letters instead of just rotating them. But ultimately, this type of cipher can easily be broken. A computer program could easily figure out text using this cipher in less than a second. Given that, you should never use a Caesar cipher in code. It's just not secure. But the reason I bring it up is to introduce a few concepts. Each cipher has an algorithm behind it. This algorithm is used for both encryption and decryption. Each algorithm typically has a key. The term plaintext is used to describe the input data. The ciphertext is used to describe the encrypted data. Each algorithm should be reviewed to identify its weaknesses. This information is critical at deciding how or if you should implement a given algorithm. Now out of the past and into some modern day cryptography. Hashing is used as a base primitive in many security operations. A cryptographic hash has the following properties. It's easy to compute. The hash value, a given hash value for any message. And when we look at the slide that I have that shows the examples for how to code this, you'll quickly go, yeah, I see that it's pretty easy. It's infeasible to generate a message from its hash. So in other words, it's not reversible. You can't just take a given hash and get back the message. Although there are hacks with dictionary-based attacks that do allow us to determine if a value is hashed, but we can't from a given value what the hash will be, and then we can compare hashes. That's a dictionary attack. It's not feasible to say from a given hash with no dictionary to figure out what the original message was. It's infeasible to modify a message without changing its hash. So if I have a message that's 1, 2, 3, and the next message I have 1, 2, 3, 4, they will have different hashes. It's also infeasible to find 2 different messages with the same hash. So a message of ABC and another message of DEF would never produce the same hash value. Well, in RAD Studio, we have currently supports 3 security-related hashing algorithms, MD5, SHA-1, and SHA-2. Although weaknesses have been found in MD5 and SHA-1, so the current recommendation for hash for security purposes is SHA-2. Although you will find uses of MD5 and SHA-1, which are widely spread, and you will also find requirements for using them with existing systems. But don't assume that by using MD5 or SHA-1 you are secure. MD5 can be broken and compromised within less than a second. Rad Studio also ships with one non-cryptographic hash called Bob Jenkins. Hashing has many uses outside of cryptography, and it should be noted that security-based hashing algorithms may be used for non-security purposes as well. So let's take a little look at this. We have, there is a class called T, well it's not a class, it's actually a record structure, T hash SHA-2, and it has a method on it called getHashString. And I can pass in it the value that I want to hash, and I also have to choose, like if I want to use SHA-256, which is just a variant of the SHA-2 algorithm based on the number of bytes. And you'll see the differences here between the Delphi and C++ code. They're very, very similar. And ultimately, we just have to use or include system.hash. And let's talk a little bit about some use cases that you'd use when you use a cryptographic hash. The easiest use case is verifying data such as a file or message has not changed. For years, people have seen hashes on files published to allow the receiver to verify the source of a given file was not changed and transmit. A few examples that are also available are storing of passwords, message authentication, and digital signatures. Let's dive into the way we store password. History has shown that it's nearly impossible to keep intruders out of your system. So it's not a question of when will they get in, it's not a question of if they'll get in, it's a question of when. So first off, don't ever store your passwords in clear text. If you hash the password when it's entered and store it, then you can compare the hash of the password entered by the user, and then you don't need to know the password. The system emails, when a system that I'm using emails me a password, when I press the I forgot button, it tells me they don't care about security of me or their customers. They don't care, and it's time for me to close my account with them and make sure that I don't use that password ever again, because it is common knowledge. There are common passwords out there that are all known to those who might hack your systems. So if a common password is used and it's given when we hash it, it's given a same hash and run against the list of passwords you have, you will see the results. So you could say, hey, the password of let me in, something simple that I know that I've seen, or ASDF1234, common password. There's a whole bunch of these, right? The common passwords, when I hash that, I can have a pre-built dictionary that can list all of the known passwords, and then I'm easily able to figure out people's passwords because of that, because I'm just comparing the hashes and I know the source data. Well, to prevent that and to make it more difficult, we introduce something called a salt. The first salt that we have, a salt is a random piece of data that's combined with your input data. Typically it's appended, but there's no reason why it can't be someplace else in the data. That first salt is stored with the password itself. And so you take that salt, and this prevents the dictionary attack from working against all your passwords instantly. However, they can still dictionary attack one at a time. It's just slower. So all we've done is slow them down. And that's actually an important thing, because the time that you get hacked, the time that it's made public, and the time that we notify users, every minute counts, because there are people going after your customers instantly. So this is what you need to do, is this helps reduce your exposure. The next one is because of that, we introduce a second salt. And the salt is in a global value that's stored separately from the password. This value is combined with the other passwords and the previous salt. And now if someone is able to get your password file and they're able to get both salts, they're still effective at getting versing a given password, but they still need one that hopefully you've stored separately, and that so you might have your passwords in a user table and a database and the global hash in a config file, and they might get the one through a SQL injection hack and not have any ability to get the config file. And so this will help reduce your exposure. And so it's important to do that. So both dictionary attacks and rainbow table attacks are common with password files, and this happens every single day. Let's talk a little bit about another way of using hashes, which is hash-based message authentication code, or an HMAC. A MAC, or message authentication code, is a piece of information that's used to authenticate a message. HMAC is basically a hashed version of that. It provides data integrity to a given message has not changed. It also provides authenticity. The message is from a source that knows the shared key. HMAC, however, does not encrypt the message, so that data needs to be secured by another mechanism with encryption before signing it with, say, an HMAC algorithm. Both sides of the system have a shared key, and it's commonly used in REST services. But I need to point out that if you say use an HMAC in your mobile application, you've probably given everybody that key. So it's just something to think about, whether you know it or not. Hey, I've been using this, but anybody can now use that key. But it's getting an HMAC in RAD Studio, however, is very simple, and it is useful, and it is a very useful algorithm for many things. HMAC is supported by with MD5, SHA-1, and SHA-2. Note that the cryptanalysis on MD5 and SHA-1 are okay and don't suffer from the same problems that you have when you implement them with just a typical hash. Because of the way that an HMAC works, there's enough additional factors at play that help keep those secure. However, if you're implementing a new system, I would still recommend using SHA-2. So as you can see here, I can call just thash MD5, get HMAC, or get HMAC as bytes, and I could do this quite quickly with all the algorithms, and it's very easy to do. Symmetric-key cryptography systems depend on a shared key. Any party that knows the key can decrypt the data by this key. The process starts with plain text. Most algorithms take the key, an initialization vector, or sometimes called an IV, or a one-ons, although not all of them use an IV. Together, these are used during the encryption process to produce the resulting ciphertext. The key and the IV both need to be used again to decrypt the data. Note that the shared key is considered secret, and the initialization vector is commonly not a shared secret. Let's talk a little bit about what's called a block cipher. So a block cipher is we have the algorithm is built and designed to work with a fixed amount of data. So with the DES algorithm, the block size is 64 bits. And if you'll notice, the key size that is also there, this is the key that we're using to encrypt, is 56 bits. DES is very insecure and shouldn't be used. However, there is a variant of DES, triple DES, that still has that 64-bit size, but introduces key sizes of 56, an additional 112, and 168. If you're needing to use a triple DES, the bigger the key size, the better. There's also another algorithm out there. There's lots of these. There's tons of different block ciphers. But AES, or Rigendell, I hope I can say that right. I've never known exactly how to pronounce it. Rigendell has a block size of 128 bits and has a key size of 128, 192, or 256 bits. And this is bits. So we have a problem. We have lots of data that we need to encrypt that's much larger than this. And so we have lots of different ways. You know, the initial thought was, hey, let's just, so we need to deal with that. So what we have is we have something called mode and padding. Mode is the method or to handling these multiple blocks of data. Another word that's commonly used is chaining for this, and basically it allows us to combine all of those blocks together into a single encrypted result. Padding deals with the fact that we work with a fixed block size, and you're not going to have data that's going to fit that block size all the time. So it deals with the last bits of data that don't fit in the block. And there are several different methods of padding that are out there. So let's talk a little bit about the electronic code book, or ECB. This is the poor man's way of dealing with this. Hey, we'll just keep repeating the same algorithm over and over and over again. So we take our given plain text in, we give it the key, we run it through the encryption, and we come back with the ciphertext. And so we've, you know, but we're on a very small bit of data. So, you know, 64-bit. We're not talking bytes, we're talking bits. And so what happens here is patterns start to happen. So this ECB, if you ever find that you're using ECB, you're totally insecure. Well, let me explain. Let's watch what happens. With this original image on the left, I found this on Wikipedia, and I just give a wonderful source here because it just demonstrates so well what ECB does. Because of the nature of it, when they did the encryption on the original image, you'll see that there's a pattern. All the white space all has the same value. And because of that, you can see what's the white space. As each color changes, you can see the color changes. So with ECB mode, I can kind of still see the image. There's data still to be found using ECB. Obviously not secure. Most every other mode out there gives you far more random image, and that's the kind of thing that you'd like to see with your data. So this is really quite telling on ECB. So we're going to talk a little bit about another method, and this is cipher block changing. This is probably the most common method that's out there, although there's many. And this is kind of, it's not a standard, but it's almost a de facto standard. It's used a lot. You take the plain text and you give this initialization vector that we have, and then initialization vector is XORed on the first bit of data. So your data is XORed with that. Then it's run through the algorithm, all right, that produces the ciphertext, and the result of that ciphertext is then XORed with your new plain text. So they're chained together. So you have to have done the first bit of encryption before you can do the second bit. So with the first one, you might have had, with electronic codebook, you can do some things like parallelization, but it's at a very big cost. Whereas in CBC, there's no way to do parallelization of this algorithm. Although there are chaining or modes of operation that are much more friendly to parallelization, you need a library that can take benefit of that. And so that is up to you to decide. And even if it can use parallelization, most of the ones I've found still don't use that. On the other hand, decryption can still be used in some of these very easily to be parallelized, because I can decrypt a given block and then deal with the XORs and that later. It all depends on the type of operation, and that's something you should be looking at. So let's look at this. ECB, that's one called electronic code block. There's no external input for each block, so it demonstrates that pattern, and it's insecure. Code block chaining, or BC, that's the one we were just looking at, takes the prior plain text, it XORs it on the result, and then continues to change that through. Cipher feedback takes the prior plain text and XORs it on the input. Output feedback uses the ciphertext as an XOR value. Counter, this is one that's more friendly to parallelization, has an incrementing counter for each one that's also involved in that. And then XEX, and there's lots of variants of all of these, including specifically this one, is an XOR encrypt XOR, which basically takes a unique value and XORs each block. Maybe this is way over what you need to deal with, but the thing I need to point out is just don't use ECB. All right, you're going to probably be fine with most of the others, but reading through each of them is good. And the other reason is I get a lot of people, I've read, lots of questions about encryption over the years from people and say, hey, I'm using library X and I can't decrypt with library Y. And they must be working differently. Well, there's lots of reasons why. One, your key might not be in the same encoding. You need to make sure that your key is in the same encoding when you're starting. Number two is your initialization vector needs to be the same, and that's not always the case. And then you also have to have the same block mode. And so these are critical to be able to encrypt from library A to library Y. And it's not always thought of very well in that respect. Padding was the other thing. Padding takes data that's too small to fill a block. Many methods for padding. We have bit padding, byte padding. There's some standards out there. One thing is there's this padding oracle attack. So what happened with this attack is it was really in the SSL and SSL 3.0, actually all the versions. But what this allows it to do during the negotiation process is this figures out if a given block is padded correctly. Well, basically you could give it data and say, I padded this data correctly, and it could figure out the padding. And because of it, this oracle definition is basically, it says, hey, I could infer bits of information about how you're encrypting because of it. So we need to be careful about what information we share. And although the padding oracle attack was specific to the padding in this case, it could be around anything. So the key has to be sensitive, obviously. Then we have an initialization vector. And this is kind of arbitrarily the opposite of what we had with that. An initialization vector can be known, and quite often is known, to the end. It's a pseudo-random value. It's critical to a streaming cipher implementation, which is basically to implement this correctly. The IV, like I said, can be public knowledge and can be sent and clear. It just shouldn't be repeated. It needs to be, so when you're dealing with the random value and say you're encrypting something and then you start over the process, you should not be using the same initialization vector. So if you're encrypting files, you can start the IV in the actual file, typically right before the encrypted data. And this is a common practice among many libraries. But let's point out Wi-Fi. If you're familiar with it, there's the WEP protocol. And it used RC4, which is a streaming cipher. It had no external IV or initialization vector. The WEP key was concatenated with the IV. And since the IV was not sufficiently random, a birthday attack, which basically, if you walk into a room and ask how many, the odds of guessing somebody's birthday are fairly high. There's a principle there that how it got that name, but you can start guessing what the IV was because it wasn't sufficiently random. And because of that, they were able to determine the WEP key. So hence the same key should never be used twice in a stream cipher. Programs freely available on the internet can hack the web protocol in around 3 minutes. I a few years ago had a security class that I was taking in, and we were required to download and actually perform this hack. And it was quite interesting to learn how to ethically deal with this and how you should avoid this on that. Let's talk a little bit about passwords and keys. Both are the way to your data. So it's important for them not to be dictionary words. It's also important that they not be hash of dictionary words. It needs to contain random data. Otherwise, it's susceptible to brute force attacks, where they try every combination of dictionary words. Swapping out letters for numbers and symbols is known to hackers, and they add these to their dictionaries when they attack. They also use combinations of various dictionary words together. So when they're doing brute force attacks. So just a thought, be careful about how you're going to do this. Another thing is be aware of where you're storing these passwords and keys. If they're in a spot that's easy for somebody to get at, then they probably have them. So the next one we're going to deal with here is talk a little bit about which algorithms are out there. So on the block cipher side, we have Rigendell or AES. Rigendell has a few additional features that AES doesn't. AES is a fixed block size. There's a couple of different block sizes that are in Rigendell, but overall they're the exact same algorithm. So if you pick AES, you're really using a Rigendell algorithm with a specific block size. Blowfish is another one. Bruce Snyder is, oh, well, I see Blowfish here twice on my screen, but there's two fish in Blowfish. And I don't remember which one Bruce Snyder's responsible for, but there's also, that's a common theme out there. RC5 is a block cipher, and then DES, which stands for Data Encryption Standard, and it's no longer the standard. So just an FYI that. AES is Advanced Encryption Standard for those who there, and they got those names because of FIPS, Federal Information Processing Standard. They put out a call and a challenge for algorithms, and multiple algorithms were picked to be finalists, and ultimately they picked the algorithms they did. There's also a concept of stream ciphers, and the stream cipher is a little different. It doesn't need, it can work with an arbitrary amount of data, and can continue dealing with the fact that data is always streaming through it. And it has some unique benefits of that. And so the SALTA 20, whether or not you realize that you're probably, anytime you use the Chrome browser to visit Google, you're using SALTA 20. It's because it's built in, it's part of one of the standards that's involved with there. And it's not really a standard, it's the way SSL and thread level TLS can work. Well, really TLS, it allows them to negotiate what cipher to have. So if both sides have it, this is which one's used. There's also something called Rabbit and RC4. Block ciphers are also, when they use the chaining and the padding, could be considered stream ciphers in some sort of way. I mean, people consider them that way. Some documentation will differ on that one way or another, but ultimately I point that out so that you can be aware of that. Notice these are just examples of the algorithms, and there's many more in each category. Let's talk a little bit about symmetric or asymmetric or public key cryptography. This is significantly different. It takes in a given plain text, and we go to the encryption process, and it needs an input of a public key. That public key can be known to everybody, hence the name of it. It is public. Then with that encryption process, we end up with a ciphertext. The only way to decrypt the ciphertext was with a private key. This private key is then used to decrypt. So I can encrypt anything and guarantee that the only person with the private key can decrypt it. And so that's an incredibly safe way to send data. And it is used all the time. Anytime you're using HTTPS, it uses what's called a Diffie-Hellman protocol, which is basically a public key protocol that allows us to take this a given the public key you have is the certificate that you're issued. You can use, well, that also contains the private key, but then there's a public that's sent with that. So as soon as you start to communicate, they send you the public key, and then you encrypt the data that you want, and you send back, and they're the only ones that can decrypt it. And this is kind of a negotiation that happens at the start of an HTTP session. So why would we use a public key versus the other? Well, symmetric keys in comparison to public keys. Well, the symmetric key has less computational or CPU cost. Public key is far more intense on the processor. It requires a higher computational cost. So it's slower. However, symmetric keys, they don't scale very well. If I have to share keys multiple places, my risk of exposure is much higher. However, public key is very scalable. It runs the backbone of the web exchanges today that are secure. With symmetric key, you can encrypt or decrypt. All right, and so with that same key. So once you lose the key, all the data that encrypted that with that key is basically plain text or available as plain text. But with public key, as long as I can keep the private key truly private and not shared, it's the only end that can decrypt. So why would I use one or the other? Well, in public key, it's so expensive, and I mean really expensive, to encrypt. Let's take PGP, for example. PGP is a way of encrypting messages that only a sender or a given set of senders can, or not senders, receivers can decrypt message. So I could say I'm going to send this message to 3 different people, and they all have given me their public key. Well, what PGP does is internally it encrypts using their public key a symmetric key. So it's actually encrypting the faster version. It's key. So it generates a random bit of data and for the key, and then stores that under public. So basically, the public key is used to exchange symmetric keys. And I know I probably really loused that up in some ways, but open with your SSL, it's doing the same thing. So once well, not SSL, I gotta stop doing that at TLS, or basically your secure web session. The first thing it does is uses the public key to exchange a symmetric key. And once both sides know the symmetric key, they're able to communicate safely. And that key that was symmetric was generated randomly at the first. So one thing about it is Delphi and C++ Builder do not ship with any encryption algorithms. They just don't. It's kind of a frustration of mine because you're forced to deal with lots of different algorithms out there, and they all have their different nuances and flavors. And we've used, the place I work, multiple variants of each of these over the years. So Lockbox. It's available in the Get It package manager. There's 2 different versions. There's a Lockbox version 2 and a Lockbox version 3. And that's kind of gives you an idea. If one's based on the original Turbo Power Code, version 3 is a complete rewrite, but just took the name. So they're actually 2 different code bases, and they're both getting maintained independently. Hence some of my confusion. Tforge is a very a nice library. It has lots of different options in there. Tori has a huge list of options right here on this web page. But one thing about Tori is a lot of those are out of date. So if, say, there's a vulnerability found in an algorithm A and it needs to be patched in some way, there's nobody maintaining some of those. So that's important. And because of that, you might want to look at something like Secure Black Box. And Secure Black Box is the only commercial product that's out there that I have seen for Delphi encryption libraries. And quite often, it's been licensed to lots of third parties that implement encryption. So it's in certain third-party code all the time. C++, Crypto++, and OpenSSL. One thing I should point out here is you are using the Clang compiler. The Clang compiler does support a new set of instructions for AES. The processors nowadays have 4 or 5 instructions that are assembly instructions that basically allow AES to be performed at the hardware level much easier and much faster. And that's really quite awesome. But Crypto++ and OpenSSL have been compiled quite often to use those. And because of that, that is nice. Also, platform APIs tend to be faster as well because they are dedicated and know and how to manage the various platform. These can also be used by Delphi as well, but you're required to convert the headers, whereas I list them here under the C++ because the APIs are easily consumable on each of the platforms. Some additional information that you might have are there's tons of great articles on Wikipedia. It's a really, anytime you get lost here, you can get farther in depth with encryption and cryptography in Wikipedia than you probably want to. So it'll get you a good start. However, one thing that I always like to be aware of is new and common ways that systems are being hacked. And the Open Web Application Security Project I found is a very nice and great resource for that. It talks a little about various different types of attacks and how you can mitigate those and what are the things that are there. And I've seen, although it has web in its name, I have seen these attacks on desktop and mobile applications. So granted, certain things like cross-site scripting are truly web-based. There are other attacks such as SQL injection or command injection that I've seen used on all types of applications. And keep in mind that as soon as you start building REST or EMS type services, you have a web portion of your application. Whether or not you would consider that, if I've got a middle tier that's REST-based, that REST-based is a web app. It might not have a user interface, but it's still got the exploitable points as before. If you want to get into far more details about cryptography and how each thing really works, there's a 6 to 8 week course on it, and it's free. And Stanford has it out there, and it's a really awesome course. Takes some time to go through it. There's also several other free cryptography courses that are out there on the internet as well. I've also listed all of the URLs that I had for the various libraries that I mentioned throughout the session. I'd like to thank you all for listening to my presentation, and for those listening live during CodeRage, please submit your questions now, and I'll do my best to answer them. Thank you.
Okay, fantastic. Thank you, Robert, for your work on putting that together. Let's see. Oh, looks like you're unmuted now.
Thank you.
Great. So I always quite a while ago I actually took an interest in cryptography and I actually learned a few things in this session. I thought I was fairly well in the know, but there were some good bits in there. So thank you for that. I heard once that the most important thing that the average person, the average developer can learn about cryptography is that it's too complicated and they should leave it to someone that knows what they're doing.
We're all forced to deal with it, and we need to continue to learn.
Yeah.
Otherwise, our companies and the people we represent are going to be having problems due to what we produce, and we see a vulnerability in the news every week, or a hack or somebody's been breached, and ultimately that all comes down to software developers. And so it is our responsibility to learn, and it's our responsibility to try to do the best we can.
Mm-hmm. So Danny's asking, what's your opinion on passwords like correct those battery staple, or it's just a string of dictionary words?
If it's used as something for, say, an encryption key, I think it's a bad idea. If you're using it for, say, a password that's on some website and it's a significant amount of length, you have some options, but you got to be careful that the rainbow tables that have been built, which is basically a combination of all the dictionary words, can go certain levels deep. They can go 4 and 5 words deep into dictionary words. And so adding symbols is significant in reducing the rainbow table attacks. Basically, it's a set of pre-computed hashes that are used to allow, once a hash has been compromised, it allows them to, or the password file has been compromised, they can use this. And so I tend to be a little wary of it. I like long passwords, and I also like that they need to be mixed completely.
So by your suggestion, putting symbols or numbers in between the dictionary words.
Yes.
Okay. Yeah, it's
now, when it comes to, say, a security key, it needs to be just random. So if you're dealing with some type of key that you're trying to generate and you want it to be a password for a given system, don't do something like that. Generate a random set of data and use it. One of the things we use quite often is a product called KeyPass. Mm-hmm. It's freely available, has a wonderful password generator in it, and it helps generate some very random, unique keys, and that way we don't have the potential of a dictionary attack.
Yeah. Yep. Delphi includes the PC1 Cipher in DBX. How good is that one?
PC1, if I remember right, I'm not an expert in cryptography. I'm more like a developer that just loves it. And I actually work with guys that are way better than this, white hat hackers. But PC1 is a variant of RSA. I believe it's a permutation of how RSA works. RSA is DES. Sorry, I'm getting my acronyms all backwards. DES. And DES is exploitable, very easily exploitable. And I would recommend avoiding anything with DES and PC1. I would not consider that secure.
Okay, that's good to know. If you know what is the difference between or the reason to use Lockbox versus DCCrypt?
Okay, that's a pretty fair question. We've used both versions of Lockbox at times. We ultimately have we've also used DCCrypt, and we've also used the platform encryption libraries. Ultimately, we use a combination of DCCrypt and the platform now, and it all came down to performance for us. Lockbox and those platforms seem to be maintained, and I don't know of any known vulnerabilities in any of those.
between DCCrypt or Lockbox, but it's preference. But one thing that should be noted is when you say, hey, some of the things that really drove me nuts with Lockbox, and I'm not sure if DCCrypt has the same problem or not, but we were trying to interop with something that was not Delphi. And the initialization vector was passed in a different way than Lockbox would have. So with Lockbox, the first, when you're encrypting, say with AES, the first few bits are the initialization vector. And that initialization vector is always required to be the first few bits with Lockbox, instead of something where you would normally pass it and you get control of that. And hence, you had to know how the implementation details a little bit with Lockbox to make it interop with some of the other libraries. But we have been successful with all of those in interop, as long as you understand that. And one of the biggest reasons for interop issues is the mode and the padding being wrong. And getting those wrong guarantees that you'll never be able to decrypt what the other library is producing.
Yeah. So Alf's asking, which block ciphers would you use if you were trying to connect from Delphi to somebody using PHP on a Linux server?
Personally, when it comes to block ciphers, I tend to go with AES 256 for almost every thing. That might really come down to the fact that I'm required to follow FIP standards, which that is the FIP standard right now.
Right.
And so that's where I go. It's supported by everything. AES is the standard.
I remember when they were debating that standard. It's nice now to have, because before that DES was the standard and it wasn't secure. So it's good that we have a good secure standard that's now endorsed and everybody's using. So if you can, use that one. Exactly. Is DCP library safe?
Every library has the potential to have vulnerabilities. It's only as safe as the known vulnerability. It's possible that it's not for anyone. I can't guarantee any library that's out there is safe. However, I know of no known vulnerabilities in DCP.
Very diplomatic answer.
But
you're right.
The truth.
It's actually that's true. It's like AES. It's secure, it's good, but then as soon as someone discovers a vulnerability, it's like, oh, maybe not. Now, actually, in some algorithms, they do some mathematical proofs, which I never quite understand completely, that show whether it's vulnerable or not. But anyway, which library is used in the HTTP client communication for the HTTPS protocol?
That is the platform-specific library, depending on if you're compiling for iOS, Android, Mac, Windows. It's all the platform.
I was actually looking at reasons to use platform-specific libraries and found that the platform actually will guard the memory where your key is stored if you're using the platform library, whereas if you're using your own library, that memory might be susceptible. So if your machine is compromised, that key could get compromised as well just by something else reading your memory.
Yeah, that is actually a real concern.
So I hadn't even thought about that. So it's a good reason to use platform libraries.
Mm-hmm.
What Delphi libraries do you recommend for public-private key management?
Open source. RSA is the only public-private key algorithm that I've seen, and it's in Lockbox. There might be others, just because I'm not seeing them. And the commercial, like Secure Black Box, they got them all. So if you're needing public-private key, that way, to be honest, we need to use PGP on a regular basis. We actually just go out and call GPG, which is the open version of that directly. So we call the actual command line. We don't embed that in our code, and it works out well for us.
That's a good idea, yeah. Stefan's saying he's read through the LDOS page, and they place an emphasis on timestamping. How does that fit in?
Well, I don't know how. I actually don't know the secure black box product very well, but timestamping typically deals with, in my understanding of it, is what's called the initialization vector. You want something that's unique, and when you're starting to generate things like pseudo-random numbers, you need to have something unique, and quite often timestamps are used in that respect. You also need to deal with the fact that data can be modified or manipulated in transit, and you need to deal with that because man in the middle, even though I establish, say, an SSL connection between point A and point B, there is still the potential of in fact, there is still all sorts of devices in the middle of you that can intercept that traffic. That doesn't mean they can be able to read it or not, but they can intercept it, and they can also interject bytes into your stream and cause problems, which causes things to be out of order. It's a common hacking attempt. So timestamping is useful in saying, hey, I got orders right on packets and things like that. The good news is a lot of that's handled like in the TCP protocol itself, but in other things that are not, say, socket-based, that's where it falls. And those are my opinions. I don't know how it applies to the LDOS kind of products.
Okay. In DataSnap server under TCP/IP, we can use RSA and PC1 filters. Can we exchange the symmetric keys, for example, with RSA and custom filters, AES 256, for example? Is there an example or articles for that case?
No, and in fact, that bugs me. One of the common things that I see is event-based, hey, let's let you encrypt the data. And what that does, I've seen a lot of examples of that where you say, hey, we're going to AES 256. And what happens is both sides end up having the same password. And as soon as you have, say, a mobile app, you've distributed the password, which basically means your app's insecure. And all that data you tried to encrypt, it's pointless because anybody can decrypt it now. Another thing with that, so most of those examples and that I don't feel, it was one that I was going to try to do for our next, the next session I'm going to do here in CodeRage, but it just doesn't work. Well, I was going to try to do it with app tethering, where we were going to do public-private key, but I couldn't get it to work. And primarily because I just ran out of time, not because it's probably not technically feasible. It's just I didn't have time. And because you do need to exchange that key through a public key mechanism, similar to what SSL does. And because of that, if you ever have the option between, if you ever have the option and control, use SSL. It's provided for you, and it works. And the next session that I cover, I talk about SSL almost exclusively. That's the primary focus of it, and how to do it client side and server side, and because that's how most of the products really should be secured over the wire.
Okay. Yeah, good. I think that's probably really good advice. Is that if you, as much as you can, use a known, proven system that, like Pramaz was talking about with patterns and parallel programming. He said the code you don't have to write doesn't, or something along the lines of the code you don't have to write doesn't have any bugs in it or something like that. So if you can let somebody else handle the complications, that's all the better than you trying to do it yourself. Any size of string can be encrypted?
That all is the algorithm, yes. Any and it's usually not strings that we encrypt. It is bytes of data, because when you start dealing with strings, you already introduce another level of problems such as encoding. And so when you're dealing with encryption, you want to deal with just the raw bytes, but the size is all dependent upon your machine and your library capabilities. And so you should be good on most any size string. Remember, like SSL, we can have an open indefinite streaming protocol coming through, and that's because we break it up into blocks, and we can break up those blocks into smaller sizes and that are manageable, and we can handle the buffering and the things that go on. That's perfectly acceptable for you to do in your code as well. So, sometimes you just need to break things up because you do have machine limits.
Right. Yeah, you always have a limitation in memory. Is there a list of Delphi sources or use cases that you can offer, for example, for securing files locally versus streaming data between DataSnap or EMS clients and servers versus working with cloud storage options?
I don't know of any actual physical examples. The reason this goes to there's a big fragmented community of too many different ways to do encryption with Delphi and no standard way of doing it. So each library has its own examples, and you have to choose, and that's kind of it's part of my frustration with that. But a simple that's why I didn't talk about physical code examples. I talked about more of an abstract of which algorithm you'd use depending on the library. And so for file storage, it all depends on the use case. We have files that we need to archive, but we never need to read again unless there's a problem. And with that, we PGP encrypt them with a public key that is sitting on our server, but that private key is nowhere to be found anywhere on the hardware. And so that's something that is there. It's also good for, hey, we're transmitting, say, a file to a given person, and only that person should be able to use it. A PGP type solution would be a good one. But if you're dealing with, we have files that we have to continually not only encrypt but decrypt on a regular basis. We go with a simple AES 256 solution with a guaranteed random initialization vector, and that will work. And as far as streaming and over sockets, like I said, SSL, but there are gotchas with SSL. The next session I talk about them. There's lots of gotchas. And so we should, and that's there.
Is there anything to support XADES XML signing?
I don't know of anything, but I don't know of anything right off that's out there right now that's on the Delphi side. But then I'm not an expert on that area, so that's something I'm not familiar with.
Okay. And I just saw the time, and it's actually top of the hour about here, so we need to get on to the next session. So thank you, Robert, and thank you to everybody for all these great questions.
Well, thank you.
And you'll be back in a few hours for the next session, which is rock solid and secure communications for EMS, DataSnap, REST, web services, and raw ND sockets, where you'll be talking about SSL.